Okay, so I was told during the break that people worry about solving these huge SDPs, and that's a valid concern. So what I'm going to do is I'm going to show you a little MATLAB simulation that uses an algorithm it's not ours really, we use as I said, the ADMM to solve this minimum nuclear norm plus lambda times 1 norm. So the alternative, the ADMM algorithm, alternate direction method of multipliers. And so I'm going to just show it to you on an example. So I'm going to make this example. So we're going to have a matrix which is 1,000 by 1,000, so a million unknowns. Fairly big SDP. The rank of the low-end component is going to be 45, and I'm going to mess up 100,000 entries. I'm going to make, this is MATLAB code, I hope it's okay with everyone. I'm going to make the low-end component by taking a d by r factors and multiply by an r by d factors. That's a low-end component. I'm going to make the sparse component by selecting 100,000 entries among a million. S is 0, except on the set I selected, I'm going to put some stuff, some random stuff.
So how you got one column of an image is 1,000.
So here's a synthetic example, right?
Yeah.
So here the number of rows would be the number of pixels.
Okay. So it's 1,000 only?
Here, I'm just making the example, right? So, and then I'm going to add them up. Okay, so let's do that. Right, so we have a problem with a million unknowns. And now I'm going to run this ADMM algorithm. That's what you see, RPCA underscore ALM for augmented Lagrangian method. No input parameters, just M. Because lambda is 1 over square root of n. And the algorithm runs ADMM. Okay. So it's an iterative algorithm. So we see the outcome at each iteration. Okay, and so we see after 7 seconds it's done. And the rank of the input was 45. The recovery rank is 45. And the relative error, like how accurately did I get this low-end component? I get 6 digits right. And then the cardinality of the corruption was 100,000. The recovered cardinality is 100,000. And so, of course, if I got the low-end component right, I get the sparse component right. Okay, so on this example, you know, we can solve it in about 7 seconds on this MacBook Air, which is not a powerhouse. Okay. Now, I can make the problem really tough, and that's courtesy of my wife. She's a statistician, so she says, well, you see, the story is that lambda doesn't depend on input size. It's a bit bizarre when you look at it. And so she says, well, why don't you just take S divided by 100? You say you should not change lambda. I want to see that that's the truth. And so we picked. Right, so now you have so what you see on the top are the histogram of the entries of the low-rank component. So roughly between minus 0.02 and 0.02. And then what you see is a histogram of the corruptions. Of course, the corruption is sparse. And so what you see is that the entries, the size of the corruption is the same size of the rank. So by looking at the entries, you would not know whether it's a corrupted entry or not, because it's exactly of the same magnitude. And now I'm just going to run the same algorithm. I did not change lambda. I still input n, because lambda is still 1 over square root of n, even though now things are in completely different scale. Okay, so all right, so now it's going to work. So you see it's searching. So you see the rank of the solution after each iteration, the number of entries it believes are corrupted after each iteration. Again, this is a pure MATLAB implementation. Remember, the correct rank is 45, 100,000 corruptions. It seems like we're almost there. And we're there. And now it's going to search the space of rank 45 matrix, and now it just, okay. Right. Lambda did not change, and now it's not 6 digits of accuracy I get, it's 8. So, okay, so you can run these things. Okay. But it's a whole industry. I mean, there's lots of people designing much better algorithms than what you see here. this is just. Okay, so we were discussing phase retrieval. So maybe I'll skip this. Okay, so what is phase retrieval? So I think this is where it connects with the work that some of you are doing. Sorry. So we have phaseless measurement about a vector x0. I'm going to write down a discrete theory of phase retrieval of a vector in Cn. I would like to take linear measurements, but I can't because of the limits on detectors. I can only measure the squared magnitude, as in X-ray crystallography and many other fields. So the phase retrieval problem is actually to solve this system of equations. So I need to find an x which obeys this quadratic equation. And that you know that it's hard. Very hard.
So how is M in comparison to N? How
right now, it's
independent?
So we want to have good recovery results, right? So how many pieces of information are there in X naught? Well, X naught has both a magnitude and a phase, so there are two n real numbers. Mm-hmm. So I'm going to need to have at least two n equations here. Right? Otherwise, okay.
You were speaking about the spatial constraints before, and now they are not sort of.
Yeah, because now I just want to speak your language now. Right, now we can abstract the problem. I tell you where it's coming from, and now I care about this.
You discard the spatial constraints, you can just prescribe any phase, right?
Right, but now is it okay if we look at this problem, like solving quadratic equations?
Okay.
Okay, is it okay?
Yeah.
Okay, and of course I can put constraints, which we will.
Okay.
If we have additional constraints, we're going to put them on, right? If we know that x is 0 a priori in some part of the space, we'll put it in, but at the moment. Okay, so, all right, so now I want to introduce what does it have to do with convexity. Of course, this is not a convex problem. And so I'm going to use a trick that I'm sure most of you are familiar with. What I'm going to do is I'm going to turn these quadratic measurements about linear measurements about a positive semi-definite matrix capital X. Okay? So I'm going to use a lifting trick, which is as follows. I'm going to write X as XX star. And then when I look at this quadratic measurement, it's actually a linear measurement about XX star, about this rank 1 matrix XX star. And I'm going to give name to these things. So this is a linear measurement against a rank 1 matrix, which is AK star. Okay? So this lifting technique turns quadratic measurements into linear measurement about XX star. And so what I can do is that I can look at the phase retrieval problem. AK, if we do phase retrieval, AK would be sinusoids, right? There would be Fourier components. We can look at the phase retrieval problem as the following problem. What I want to do is I want to find a matrix X, which is compatible with the measurements, which now are linear. But X is XX star, so it's positive definite, and it has rank 1. Okay, so the phase retrieval problem is really a mean rank solution, exactly as we've discussed before. When I want to find a matrix with minimum rank, since we know the solution has rank 1, and is compatible with this. Okay, this is combinatorially hard. It's a different way to look at the phase retrieval problem. It's combinatorially hard. And so what you just do is you say, well, the rank is too hard to deal with. I'm going to replace it with a trace, which again is a convex surrogate for the rank. So I'm going to replace the rank constraint by the trace constraint, and we propose to solve this semi-definite program in the context of phase retrieval, which is a semi-definite program where we've used the proxy for the rank here. Okay, so this is phase lift. This is what we call phase lift. This is a bit bizarre when you look at it before, because as you were saying, at least coming from our point of view, you have perhaps an overdetermined system of quadratic equations over here. You turn it into something which is highly underdetermined. But we've just spent an hour on matrix completion. Now you know that the answer has low rank. So, well, maybe even if it's underdetermined, because I have a low rank solution, maybe I'm not that underdetermined after all. Now, I'm sure this is something that all of you know, that what we're doing is we're relaxing quadratically constrained QPs. To my knowledge, but maybe people know better in this room, it was first proposed by Shor in '87, where he was interested in lower bounds on non-convex quadratic optimization problems. It's similar to the Shor relaxations. I got to know about these techniques through the Goemans and Williamson seminal work on max cut. And then, of course, in the book by Bertin and Mirowski, there's lots of turning quadratic equalities into linear equalities about matrices. There's a whole chapter about this. What's interesting in the phase retrieval problem, nobody thought about doing something like this. I have to note that in the case of in error imaging, my colleague George Papanikolaou from Stanford proposed something similar. Okay, so this is the process. We're going to solve the phase retrieval problem by solving this instead. Now, what's nice about this is that now that you have a framework, you can explain. You can, of course, in real life, data will be noisy, so you don't get exactly quadratic equations. You get data about quadratic equations. So, for example, you may have Poisson noise, which is typical in imaging experiments. All right, so now you do not get to see exactly mu, which is a dot product between A and the object of interest squared. You get a random variable which is distributed about mu. And so if you were to do maximum likelihood estimation, what you would do is you would maximize the likelihood of the data subject to these constraints. But that's impossible to do. And so what you do with the phase lift approach is you just replace, you substitute this thing that is completely untractable by something which is tractable, where you minimize minus the log likelihood plus your rank, your convex proxy for rank, subject to constraints. Okay, so it's, if you want, regularized maximum likelihood estimation in augmented space. Okay, and so just to answer the questions that were aired, if I know a priori that the support is in STEM, I can put them as constraint to my SDP, and it will make only things better. Okay, so when you actually do this in real life, it works extremely well. That I was very surprised with this. So we took signals of all kinds. Here what you see is you see a low frequency signal. Here you see a random signal. That's just basically random noise. So X is random noise here, and here it's a low frequency signal. And then we try to recover them from 4n quadratic equations. So these have two n unknowns, right? So we measured ak.x squared equals bk. So x is in Cn, so there's 2n real numbers I care about. And I took 4n equations like this, and you solve this program. And when you get this, you get, in blue, you get the original signal. In green, you see the reconstruction, and they completely superimposed. So as soon as the number of quadratic equation is 2 times the number of unknowns, it seems to work perfectly, which is a bit surprising. No matter what x is, because of course, well, no matter what x is. And then maybe I'll skip this in the interest of time. Of course, it is not interesting to have a method that works well when there is no noise, because in real life you always have noise. And maybe I will not explain what these curves are, because maybe this is not of interest to this audience. But what I just say is this. It says you have nonlinear measurements. You have a highly nonlinear recovery procedure. And what you get is you get the stability, you get the kind of MSE versus SNR curve that you would get if you were to solve a well-conditioned least squares problem. Okay. All right, so we've got this nice linear relationship between the mean squared error of recovery and the SNR, which is what you would get if we were to solve a very friendly least squares problem, even though the data is nonlinear and the recovery method is, of course, absolutely nonlinear. Okay, and so that's what this is saying is at high SNR you have you do very, very well, and at low SNRs you have a very smooth, very graceful degradation of the quality of the recovery, which means that you can look at imaging, right? And so what we can do in collaboration with Stefano Marchesini is that we can actually image stuff that is fairly complicated from faceless measurements with these techniques, and we get good results at low and high SNR.
Yes. Is it this good performance? Is it related to the fact that you're actually doing quasi-maximum likelihood? You replace the true likelihood by Gaussian and then optimize?
Yeah, I mean, this is so this is done by plugging, I think, this pictures are done by plotting actually this is Poisson noise, so we're actually solving this.
So you're doing quasi-maximum likelihood for the noise.
Yeah, but in augmented space.
Yeah.
How many quadratic constraints do you have exactly to n?
In these experiments, yeah, 4n, something like that. Yeah, 4n. Again, one thing I'm not showing you is these phase transitions phenomena, which are again there. That is, you go a bit below 4n, it completely fails, and above 4n, it always succeeds. Something like that. I don't know where the cutoff is, but something
So
like that.
the system is overdetermined, but the matrix X capture the fact that you have a degree of freedom, and then if the noise is small, you go to the rank 1 matrix. That's basically the
Yeah. I mean, well, I'll try to answer this question in a minute. Okay? Yeah. So typically, if you solve the phase retrieval problem and you do not get to see, what you do out if you don't get a rank 1 solution, you extract the best rank 1 approximation and you claim that this is your signal. And that's how I plotted these curves, these MSE curves, by doing this. Okay. All right, so it seems to work well in practice. Okay, and so you can do low, high SNR, and it seems to work well. Okay, now maybe I'll skip this because it's not of interest to you. So let's talk about some theory now. I'm going to try to keep it simple. So suppose everything is real valued. You don't get to see the signs of these equations. So each time you take a measurement, you don't know whether you're on this plane or on this plane. And you make a new measurement, and again, you have this ambiguity. I mean, you know all of this, right? So, well, you have each time you have a pair of planes, you look at the polytope, which is the intersection. You know the solution is one of these vertex, but you have no idea which one it could be. And when you have complex data, this is your field. Well, actually, these are not pairs of planes. They are algebraic surfaces. You need to find a point in the intersection. It's extremely hard. Okay, so now let's do a bit of theory, at least the theory I know, and again, the theory is a bit incomplete here because it's very recent. So, okay, so now I have quadratic equations that I wish to solve. They are like here. And I'm going to take a simple model. I'm going to say that these quadratic equations are random in the sense that I have generic equations where these AKs are point randomly sampled on the unit sphere of Cn if we do complex valued stuff. And let's say we do complex valued stuff. So I'm giving you random generic quadratic equation, okay? Where each time the AK is a point on the unit sphere. Okay. And what is the main theorem of this part is that let's assume that m is a constant. Now is my wiggle, so it's a numerical constant times n. And in practice, we observe that numerical constant is 6 or 5 or forgot something like that. It's m times n. So with a probability which is a failure which is exponentially small in the number of quadratic measurements, what the theorem says is that no matter what the signal is, the only point in the feasible set, I don't even need to minimize a trace, the only point in the feasible set that is ax equals b and x positive semi-definite is xx star. There is no other point. So just by solving a semi-definite feasibility problem, I will recover the signal with no error whatsoever. Okay, so this is the result. Give me a number of quadratic equation which is proportional to the number of unknowns with a failure, a probability of failure which is exponentially small in the number of equations. So for practical purposes, the probability of success is 1. Then there is only one point in this feasible set, and that's xx star. There is no other. Okay, so you can solve the phase retrieval problem exactly. To have injectivity of this map, it was proved by Edidin, who works in algebraic geometry, and Balan, Bodman, and Casazza, that you need something like 4n minus 2 measurements. And so what this shows is that if you're a little bit above 4n minus 2 measurement, then you're in this extraordinary regime where actually the solution is the only point in the feasible, in the semi-definite, in what you call this, a spectrahedron, or in the spectrahedron. Okay, so this is the only point. Okay, and so at the first sight, this result is a bit bizarre again, like the matrix completion result, because you say, well, the positive semi-definite cone, we know how it looks, it's very fat. And then this feasible set is also very fat, and so let me draw both of them. And, well, here we have the positive semi-definite cone, it's all the inside, I have the feasible set, it's enormous, and I can see that the intersection is not a single point. I can see it. Well, yeah, but now this, we're looking for low-rank solutions. And so now we have to remember that, well, the rank 1 solutions are on the shell, on the boundary of this thing, right? And so they're like somewhere here or here. And now we can start to see that maybe we could be lucky. Maybe if the feasible set is well aligned with respect to the boundary of the positive semi-definite cone, maybe I have a chance to be tangent. Okay, so the rank 1 matrices are on the boundary. They are extreme rays of the PSD cone, of course. And so maybe there's a chance. Okay, and that's an accurate picture of what's going on. Now, my mental picture, the one I keep in mind all the time when I try to prove stuff, is something like this. I take a rank 1 matrix, and I perturb it by adding a symmetric matrix. And if I draw a perturbation H at random, and I look at, are you positive semi-definite? Of course you're not positive semi-definite, right? Because one eigenvalue is 1, all the other are zeros, and I'm going to get a few negative eigenvalues. Try another perturbation, I'm not positive semi-definite. Try the third one, you get the idea. There are only very few perturbations that would maintain positive semi-definiteness. And here's my pictorial representation of what they are. This is saying that the positive semi-definite cone is extraordinarily pointy around rank 1 objects. And now I have a feasible set, which is enormous, but because this positive semi-definite cone is extremely pointy, it's easy to become tangent. Now, of course, this is whole n waving. And again, the proof of this fact that with a number of quadratic equation, which is proportional to the number of unknown, this is the only point in the feasible set, is not easy. Okay. All right, so now maybe I'm not answering your question, but let's do a simple recovery algorithm. Suppose now I have noise. So now, as I said before, I'm not even going to try to do something fancy. I'm not going to try to do log likelihood regularization. I have bk, which is distributed about x dot ak squared. I'm going to do the simpler thing. Just try to minimize the misfit subject to positive, being positive semi-definite. So I solve this SDP. If I'm not rank 1, I extract the rank 1 component. Okay, and that's my x. I factor it, and that's my x. Okay, and when you do this is extremely simple-minded, and you say, well, it's way too simple. And what you can show, and what we did with Zhao Dongli, is that in the setup where we have random equations, there is no method that can do better than this, in the statistical sense. That you cannot produce a method that would have a lower mean squared error, a fundamentally lower mean squared error than this. It's at the information theoretic limit, so to speak.
X is emission?
Yeah. Yeah.
So complex.
Yes. If you care about complex, yes. Yes.
X also is.
Right. X is emission. Positive semi-definite. Okay, so in some sense, here we've got both the exact and the stable recovery that, you know, I don't know. You cannot find a method that would be dramatically better than this. It's just not possible. It's an information theoretic limit.
So the first thing would be to balance with a nuclear norm of X also, right?
But it's already there, right? I mean, it's, you see, you could, but you see, we have this theorem, right, that says that we don't need the nuclear norm because the feasible set has only 1 point. Okay. So now what you can say is maybe I can try to push it a little bit. It says, well, since it, you know, but we don't really need it in this case. Okay. All right. And the reason, I mean, the way the proof goes is that because this coin is extremely pointy, now you have some uncertainty in the measurement, so you don't know on which planes you are. But these planes, when they don't deviate too much, well, you see, you have a certain data uncertainty, and so you minimize this, and you know that you're going to be in this thing, and this thing has a small radius because this point is pointy. You know, the thing that would be a disaster, you would get a terrible mean squared error if all of a sudden by perturbing the plane a little bit, you could go far away in the cone. But you can't do it because this cone is extremely sharp. And that's why you have stability. Okay, and so this theory that I'm not showing you, this noisy theory, predicts extremely well this performance curve we see when we look at SNR versus MSE. It explains these behaviors that we see again and again when we make experiments. Okay. Connections with GraphQL. I think this is kind of nice. So after we wrote our paper, Valsberger, Dapperman, Mala got interested in this, and they proposed a related algorithm to do it, which is called phase cut, for reasons you'll see. So they start with a different approach. They say, well, suppose we want to solve, so now I hope everybody's okay with the notation, ax squared equals b. We know what it means. Like it's a vector ax, look at all the components, take their magnitude, square them. I need to solve this, right? So they looked at phase lift, and they say, well, there's maybe another algorithm we could run, and it's going to be inspired by max cut, because they say this is a max cut problem in disguise. Okay, so here's what they say. They say, well, what I need to do is I would like to find the phase of the measurements that are missing, u. So B, if B is a diagonal of matrix which has the measurement on the diagonal, then what they say is, of course, what I need to do is I need to try to find those phases u, which are vectors in Cn with unit norm on the circle, such that, well, the discrepancy between Ax and the data multiplied by the phase is as small as possible. Right? So here's a way of trying to guess the phase, so that Ax is now equal to b 1/2 times u. B, the vector b times the phase. Okay, so now they say, well, the problem we need to find is to try to find those phases. And so I need to find this complex numbers of modulus 1 that best predicts Ax. And of course, the modulus is what I measured. Okay, well, they say, well, if I knew u, then it's very easy to solve for x because it's a least squares problem. Okay, so that's obvious. So I'm going to introduce a little bit of notation. It says, if u is known, as soon as you give me u, I know x because it's a solution to a least squares problem. So let's plug in this solution. So I eliminate the x variable because I know once I know u, I know x. And so what we're left with is with minimizing the size of this matrix times u. Well, this vector, the size, the squared norm of this vector, matrix times u squared, which I'm going to rewrite this in this form. And now, of course, this u is still my vector of phases, which is unknown. So u still is u in Cn, and the modulus is 1. Okay, but now I think for some of you it's completely obvious what's going to happen. I say, well, now I'm going to look at this. So this is, this is trying to guess the phase, and right now I'm solving the phase retrieval problem exactly. And so the problem is try to find u such that it's in Cn, but it has modulus 1, so that the trace of this dot product is maximized. Okay, and so now let's write again this same problem with using suggestive notation. So what I need to do is I need to minimize the trace of this matrix times u, where u is this matrix u star. So what is this matrix? U is positive semi-definite. It has rank 1. And I see 1 on the diagonal because what I see on the diagonal is ui squared, which is 1. And what is this? It's max cut. Right? So it's max cut, obviously. And so what you do is you drop the one constraint, and you say, well, I'm going to try to solve the phase retrieval problem by max cut, where I'm going to try to minimize the trace of this matrix times u under the condition that u is positive semi-definite and the diagonal of u is 1. Completely different, completely. Once this connection with SDP is established, you can think about other SDPs to try to do the same thing. And this is 1, and its formulation is different, right? We have phase lift, which minimizes the trace of x, subject to x is positive, semi-definite, and these linear measurements hold. And then we have phase cut of Valsberger and all, where it's really a graph problem. You might try to maximize this linear function of u, subject to u is positive, and the diagonal of u is 1, and it's really a graph problem. Now, which one is better? They are different. They are different. They don't return the same answer.
PC is better.
PC is better. It makes more information. It takes more structure into account, right? Well, the equivalent, when they work, when one works, the other works, and vice versa. It doesn't mean that they're the same, right? When they don't work, they return different answers. But when they work, they have the same operating regime. If the columns of A are linearly independent, which is a very mild assumption, then whenever phase cut is exact, phase leaf is also exact, and vice versa. It's not a trivial result. It's not my result. It's the result of my graduate student, Vlad Voroninsky. Iran and colleagues, they showed that this direction, when phase leaf is exact, phase cut is exact, that maybe the regime in which phase cut, maybe that's your intuition, is larger, but in fact it's not. There's an implication in the other direction, and they have exactly the same operating range.
If rho has no, if A has not full column rank, then the projection matrix must be redefined in terms of more pendulum.
Yes.
Right?
Yes. But A in practice will all has, because it's like A is tall, right? I mean, you have more measurements than N, so A is tall. So, yeah. Okay.
Emmanuel, so if I were to think in there, this matrix B1 half Q, B1 half, I mean, in your ensemble, you're picking the A's, the columns of
This is independent of the.
No, I know.
Right.
But you're picking the columns of A randomly. So somehow is that in a particular statistical ensemble, B1 half, Q, B1 half? I mean, is it?
Yeah, there's a graph behind it.
So Q is your least squares projection, right? So Q is this.
Right. So if I pick
So Q is a projection onto a random subspace.
Sure.
Really on the Grassmannian, with a uniform measure on the Grassmannian.
There is a graph behind it.
So
So
then
Q is a projection on.
so it's a uniform projection.
Yeah, because the orientation Q is this, right? It's a projection. It's Y minus a projection onto the range of A,
I see. So it's a
which is uniform.
A.
So Q is really you pick a subspace on the Grassmannian with uniform probability, and you project onto it. That's what Q is.
So in which sense is this max cut? Because in max cut, your U is a real matrix, and your U is not a real matrix.
Yeah.
It's a Hermitian matrix.
Yes.
So there's a bit of difference.
It's tougher than max cut, but it has the flavor of max cut.
Okay.
It's like you try to find the phase plus or minus 1. In the real case, it is max cut. Here you're in a slightly more complicated where you're on the unit circle, but I think, in all fairness to the max cut people, we have the right to call this a max cut problem. It's the extension of max cut to the complex world.
And you retrieve the phase by looking at U, the solution matrix.
Yeah, because when phase lift or phase cut succeeds, well, you will have rank 1, and it has, you get everything. Yeah. Okay. So this is, there are two approaches, they're equivalent, and they're equivalent not under the Gaussian model, but under any model. Like when one succeeds, the other succeeds. That is, once you have, suppose you have the exact solution to phase lift, you can use it to construct the exact solution of this and vice versa.
I have a naive question. What is it that gives you confidence that the rank condition is generically achieved?
Which rank condition?
The one you drop, so you've got the rank condition which gets thrown away.
Yeah, well, that's the magic of these things, right?
So is there any any theoretical underpinning for that?
But the best way I see this is that what's in my head is this always, that the intersection of the feasible set with the positive semi-definite cone is unique. And it's unique because there's a rank 1 point in the intersection. And the minute there's a rank 1 there cannot be any other intersection. That's what I have in my head. I don't have anything else. Now I have proofs, which are difficult.
But wouldn't be the advantage in using the phase cut be that you can compute this relaxation, and then from there you can use this approximation result for a feasible solution within this factor of 0.8. do this Gumans-Williamson approach.
Yeah, but here the Gurmans-Williamson, it's a slightly different matrix, right? I mean, for Gurmans-Williamson to work, the matrix needs to be diagonally dominant. It's a graph Laplacian that makes everything work. Here we don't have a graph Laplacian. We have something which is a bit more nasty.
I have another question to this Voronovsky result. So it says, sorry. So if in one case the solution is of rank 1, it means if and only. So this is an if and only statement. But in the other case, it's also rank 1. So if the solution is not of rank 1, then is there any?
Then I cannot claim that the phase cut is exact or phase lift is exact.
Yes.
Being exact means there's one unique solution to the SDP and it's a correct one.
Yes. So if it's not exact, so could the objective values, are they comparable, or could it be the case that in one instance the phase cut gives a better minimum than the other case?
So that I've not studied, right? So then what you're asking is, so this is, there are simulations suggesting that for when you have noise, for example, where you don't have exact, and so you just use your guess to produce a good solution, that facelift is a bit better. It's been reported by the same people, by D'Apremont and so on. And so that when you look at their MSE curve, it seems that facelift is a bit below the phase cut approach. But sometimes one is better, something it's just comparable.
Do you have applications when your bases come from a finite set? Like
Which basis?
your U's are actually not the spectrum is not a continuous one, a discrete one. Then your U, if you recover it exactly, has a physical meaning.
So you say that you know that the phases can only be in a finite set?
Yeah.
I don't have anything on this in this direction.
I imagine
this is a very young subject, and so what you see here is, well, I know a bit more than what you see here, but not a whole lot more.
I imagine in quantum physics you could have that kind of phenomena.
Yeah. Okay. All right, so that was story number 2. So matrix completion and robust PCA, phase retrieval. Again, I think it's clear that semi-definite programming is useful, I hope. In fact, when we produce these pictures, like the people, they look at us and they say, wow, my pictures. Oh, it's great, Okay, so lecture 3. Okay, so I have to be mindful of time. So this is my last, so again, we've been missing entries, corrupted entry, missing phase. Now we're going to do something which is even, I think some of you care about this. We're going to do something which is even more ambitious, which is going to miss a lot of the spectrum. So for those of you who may not be interested in the special application, which is super resolution, I think what we're discussing really is how do I recover a measure from its first few moments. That's really the problem we're going to talk about. Okay, so this is joined with a wonderful student, Carlos Fernandez Granda from Stanford, who is working with me. And again, I have always this kind of slides to motivate what we're doing. So people know about diffraction, I suppose. Okay, so every system, imaging system you can build is subject to the laws of physics, the laws of diffraction. And so, of course, it limits the resolution at which you can observe objects. And in particular, light will have to go through a pupil element, and the fact that lights are going to go through a pupil element means that it's going to give an ultimate limit of resolution, which we're going to discuss. So, in any optical imaging system, diffraction imposes a fundamental limit on resolution. And what that means, it means that when you have a source, a spike, at a location tau, and you wish to image it, be it with a camera, a telescope, a microscope, whatever, this source will not appear like this, it will appear like this, which is a low-pass version of the source. Here, a sinc function. Okay. People know about this, right? Or maybe not. Okay. All right. So the point is that because of an imaging system looks like this, which you have the real world, which is F, which you would like to observe, but you cannot observe it. You can only observe F convolved with what people call the point spread function. In the Fourier domain, the Fourier transform a convolution into a multiplication. So in the Fourier domain, you observe the spectrum, which is a product between the transfer function, the Fourier transform of the point spread function, and the spectrum of the object you care about. And what happens in imaging system is that if the frequency is above a frequency cutoff, which we're going to call omega, then the transfer function vanishes, which means that in your data, you have absolutely no frequency information. You only get to see the low frequencies. Simple enough. And if I had a pupil element, which was circular like this, then that's the value of the transfer function in coherent imaging. The point spread function would be this famous airy disk. And so if I were to plug a cross-section of the airy disk, I would see something like this. And what that means, it means that a point source in the sky, let's say a star in the sky, will not appear as a point source, unfortunately, but rather as a big blob like this. Okay. And all right, so again, it's fortunate that we're in England. What would we do without British people? I don't know. So we have a point source, and we cannot observe it perfectly. We can only observe a low-pass version of it, and that's the notion of the Rayleigh distance. And what is a Rayleigh distance? Is the distance between the peak of the point spread function and the first zero crossing. That's what Lord Rayleigh called the Rayleigh distance. In fact, that's not the definition he used. He used a more intuitive definition. He says, I have 2 point sources that I'm going to see through my microscope, and I'm going to bring them closer. And the minute I cannot detect whether there are 2 or 1 point source, that's the notion of Rayleigh distance, which is the same. And so this is due to Lord Rayleigh. Okay, so what is a super resolution problem? The super resolution problem is you have low pass data that looks like this, and you want to invert it to super resolve the location of these events. Okay, so it's a deconvolution problem. Equivalently, in the spectral domain, it's a very scary problem. I have the spectrum, the Fourier transform of this object, which we see here, but because of physical limitation, I can only observe the low frequencies. And so what are you asking me? You're asking me to kind of extrapolate the spectrum and recover the wings. So I hope you can see the connection with a lot of the stuff you do now. Like you see the first few moments, and then you need to recover all moments. Okay, so this is extremely improved. Okay, so maybe this is a connection with compressed sensing, which I'm not going to talk about, something we worked about on earlier. So let's. Okay, so there's an enormous activity around super resolving point sources. For example, celestial bodies. So you would like to locate the location of stars extremely precisely because you want to test cosmological models. We're working with a group at Stanford on single molecule microscopy, which I'll say a few words about. The super resolution problem is the same as the spectral estimation problem in signal processing, where now you want to identify frequencies from time measurements. And so it occurs everywhere. So we're going to focus on super resolving point sources because of a number of applications in radar, spectroscopy, medical imaging, astronomy, geophysics, and so on and so forth. As I said, we're working with W.E. Murner, we're working on super resolution microscopy, where we have fluorescent molecules, and we would like to locate them extremely well in the synapse, but we can't because under the microscope they appear to be enormous, a size which is much bigger than their real size. And so the resolution is much coarser than the size of the individual molecule. We have low-pass data, and super resolution is can we beat the diffraction limit and super resolve those guys. Okay. Okay, so now I want to jump into the meat of this third part. What we've got is we've got a signal, and we said we were interested in super resolving point sources. So now we have a signal which is a superposition of point sources on the real line, or let's say on the unit interval. And so what I've got is I've got a signal which is a superposition of Dirac's with amplitudes AJs at location tau j's. And that's my problem. The amplitudes are complex, the locations are arbitrary, and so that's the thing. And now we're going to model the information we have about this object, which is like, well, I only have low frequency coefficients, and so here are my moments. Now they are trigonometric moments instead of being perhaps the moments that this audience uses, but it's essentially the same thing. Right? So now I'm going to observe moments of this measure, of this sine measure. I'm going to measure the Fourier, so this is what we're going to call a spike train, and we're going to measure the first few Fourier coefficients of this spike train. All right, so we're going to measure Fourier coefficients by the usual formula, but now k is a integer, but now I'm limited in, I have a frequency cutoff which I can only see the first few moments. Okay. Right. Now, because I have only information about the object between frequencies at frequencies up to f low, low meaning low resolution, what we know from optics is that, well, I don't have any right to talk about resolution below 1 over this frequency, which is the resolution limit imposed by the microscope. Right? There's a resolution limit, which is 1 over the frequency cutoff, and beyond this, below this Rayleigh limit, I don't have any right to talk about the details of the signal because I don't see them.
But I know the resolution limit.
What?
I know the resolution.
Yes, because that's, yes, that's,
No.
right. And yet, we're going to ask, can we resolve the signal beyond this limit? And as I said, if I swap time and frequency, I don't know if people are familiar with the spectral estimation problem, but if I swap time and frequency, what I'm asking, you're going to see sample of a waveform in time, which is a superposition of sinusoids, and I'm asking you to resolve the frequencies extremely well. And that's a spectral estimation problem. All right, so our problem looks like this. I've got a few spikes on the left, a few spikes on the right, but I only have low frequency data about this, and I'm asking you where are these spikes? And I know it's a horrible suspense, so here they are. Okay, so these are where the spikes are. And now we need a method to recover the spike. So now, of course, again, is this your area a bit? Well, I've got some sort of algebraic equations about this, right? But except these are very messy equations, right? So I need to recover AJ and tau, and so I have algebraic equation, and I can entertain the idea of algebraic methods for solving for tau and A. But being a series of lectures about convex programming, and in particular semi-definite programming, we're not going to use algebraic methods. They're not very robust when you have noise and so on and so forth. So we're going to use ideas from convex programming again. And the ideas cannot be simpler. Again, embarrassingly simple. You want to recover the spikes from very few Fourier measurements, from very few moments, trigonometric moments. What do? What you're going to do is you're going to try to find a sine measure whose total variation norm is minimum and is consistent with your measurements. What is a total variation norm of a measure? Well, it's a continuous analog of the L1 norm. If I was on a grid, it would just be the L1 norm. And the total variation of a measure, so the total variation measure of the total variation norm of a probability measure is of a probability measure. 1. The total variation norm of the sum of two probability measure is 2. Right, so it's basically the sum of the amplitudes of the thing. It's a continuous analog of the L1 norm. So if this signal was, it really is a total variation norm, is a norm that probabilists use to kind of measure distance between probability distributions. And so it's really the L1 norm. it's like if x was a measure of this form, the total variation will be simply the sum of the amplitudes. Now, for the first time, we look at a convex optimization problem, which I would not know how to solve because it's infinite dimensional, right? Because my spikes are the real line now, so I will have a norm. This object is infinitely dimensional in nature. But yet I can still think about this convex optimization problem. And then if you have noise, well, you're going to relax. You're not going to say y equals fn. You're going to trade off between the goodness of fit, as you suggested, and the total ratio. So that's the proposal. It's very, very simple. All right. So now we make this we compute these very few trigonometric moments. K is below the frequency cutoff. And the result is this. It says, I solve this optimization problem that knows nothing about nothing. It's just trying to find a signal with minimum total variation that is consistent with these low trigonometric moments. And what it's going to do is going to say, if your measure had spikes which were separated by twice the Rayleigh distance, then the solution to this optimization program is unique and exact. So that is that you have your signal, okay, which is a superposition of spikes. You have no idea where they are, what the amplitudes are. You solve this problem, which really knows nothing about even that you're going to try to recover spike train. And the result is something like this. It's like if the distance between consecutive spikes is twice the Rayleigh distance or more, then this optimization problem returns the right answer always. It's not random anymore now. There's nothing random about this. It's a deterministic result. The minimum total variation is exact. It works. It will locate this spike with infinite precision, which I think is a result that, at least for me, is like I know how to prove it with Carlos, but it's bizarre. That is, I don't understand why it puts the spikes exactly at the right location and not a bit before and not a bit after. I don't understand it. I can prove it, but I don't understand it.
What is the value of the regularization parameter? For the
No regularization parameter.
You have a lambda.
I assume I have no noise.
No noise.
No noise for now. Okay, so it recovers the sign measure or the spike train exactly. So you achieve infinite precision, which is a bit bizarre. It works whatever the amplitudes are. You don't need... Well. So you say, well, what is twice the Rayleigh distance? Well, how many... If the spikes need to be... So suppose we have n Fourier coefficient, n moments. Well, how many spikes can you have? Well, if they are twice the Rayleigh distance, you can have as much as n over 4 spikes. So you're going to have to... From n linear equations, you're going to manage to recover perfectly n over 4 events. So for those of you who follow bit compressed sensing, is that the number of measurements per unknown is extremely low. And then we have counterexamples that if I try to put the spikes too close at the Rayleigh distance, then the method will fail. I can construct examples for which the L1 solution is not correct anymore. Algebraically, it might still be possible to recover them, but not by this method.
The spike train is in a regular grid. Can you put that there? Or you have a lower bound on the distance. The distance is constant?
The distance is really what it needs to be, right? I mean, it's a Rayleigh distance.
No, I'm sorry, the distance between two spikes.
Right.
If you have separation distance of two spikes, is at least double of the Rayleigh distance.
Yeah, it's double the kind of
So
the...
this is much more general than if you know that the distance, the separation distance is constant.
Yeah, I think if you try to put them on a grid, I don't think it's going to help very much. I think when spikes get too close, for a reason that I'm going to explain. Okay, so from the point of view of compressed sensing, it's people don't know about compressed sensing, so I should go fast. But you know what the condition that people use to show the correctness of L1 is a low coherence assumption, or the fact that columns of the matrix A are almost orthogonal to each other. Here it's the reverse. We're trying to solve a problem, and when I look at the columns of my Fourier transform, because spikes can be infinitely close, the coherence is 1. So it's actually a perfect L1 recovery result under extreme coherence, in which the coherence can be 1, which cannot be explained by the current sparse recovery literature. So
Using algebraic technique, we need n over 2.
yes. Yes. If you use algebraic techniques, you can recover n over 2 no matter where they are. But there's a catch. And what is the catch? You better trust the 32 digits of your measurement. Okay. So there's a separation condition. In the discrete setting, there's a related result by Jean-Pierre Cahan, which maybe I can explain offline, which is not as sharp as what we've got in particular. It does not allow you to pass to the continuum, but it's a great result. And so we have this exact correctness of L1 under coherence equals 1. So let me explain the distance condition. So the distance condition, algebraic methods do not need the distance condition. But on the other hand, here is a very sparse signal, which is on the left. It's very sparse. And you see its spectrum on the right. And on the right, you see this is a log scale. So when you see that this signal has no energy in the low frequency part. It's very sparse, but has very low energy in the frequency part. Now, if you only measure the low frequency spectrum, which is here, how can you pretend by any method whatsoever that you can actually guess what this signal is? Right? So you would need to have a correct tens digits in your measurement to be able to do anything, which of course is unrealistic. On the other hand, if I take these spikes and I separate them a little bit, then what happens on the right-hand side is that the spectrum spreads, and then all of a sudden now I measure stuff. And the signal the moments, if you will, do not vanish anymore, right? So here we have a sparse signal whose moments vanish. So I cannot recover it if I have a tiny bit of noise. And here, as soon as the signal, the spikes spread a bit at the Rayleigh distance, then the signal cannot completely vanish at low frequency. And so that's why, even if you had an algebraic solver, you would need the separation condition. Otherwise, you have unstable results. Now, there's one guy, a hero of mine, who understood this extremely well. And in fact, he understood this picture extremely well, and that's David Slepian, who spent a great deal of his life working on correlate toroidal functions. And I cannot really talk about his work, but basically the message of his work is that if the distance between the spikes is below the Rayleigh constant, the Rayleigh distance, then you have the ill-posedness of band-limited extrapolation. Like it's extraordinary ill-posed. Okay. And so L1 needs this separation condition, but you need it for stability anyway. And so, okay, so robust super resolution of arbitrary sparse signal is impossible. That's in contrast with compressed sensing. And so we can only hope to super resolve signals that are not too clustered, and that's what the L1 norm does. Okay, so I don't really want to take too much of your time. I will say that the proof is extremely algebraic. So the method is not, but the proof is algebraic and uses ideas from harmonic analysis also. And I'll say you why is this result true. So you can show that the recovery is completely exact. To show that you actually recover this true measure from few Fourier coefficients, what you need to show is that you go through duality essentially, and what you say is that the recovery will be exact if and only if I can find a trigonometric polynomial which is low frequencies, which only uses the frequencies I got to see. So it's a low frequency trigonometric polynomial that interpolates the sign or the phase, if you will, of this signal. And anywhere else, it's between -1 and 1. So it needs to strictly interpolate the sign and be strictly between -1 and 1 everywhere else. And from this, you see two things. Number one is, if the spikes get bunched up you're going to have to oscillate very fast, but you're low frequency polynomial. So how can you do it? So you can't do it. And that's why L1 fails when the spikes get too close, because it is not possible. But duality will say the sparse signal is not the solution because I cannot construct a low frequency polynomial that would oscillate between the signs. Okay. Another thing that you see from this is, of course, what you need is how many conditions. So I need to interpolate the sign. That's n degrees of freedom, and the derivative needs to be 0. So that's another n. So you need at least 2 and a number of measurements, which is twice the number of spikes. And they cannot be too close. Okay. And so the proof consists in building such an interpolant, and unfortunately, there's no easy way of doing it. And so what we're doing is we're building such an interpolant and showing that it is the dual optimal solution, and that requires a lot of analysis and harmonic analysis. Okay, so this extends to higher dimensions, so this is not a result that has to do with one dimension only. Now you can have sources in the plane, and you just go as before. You measure you have low trigonometric moments of sinc sources that are now distributed in the plane. Again, you have the same notion of resolution limit, which is a frequency cutoff, and now it's like measuring moments of a measure that lives on the plane, and the result is exactly the same if the source in the plane are separated by something like twice the Rayleigh distance, then the recovery is exact. So you will locate these sources in the plane exactly. All right.
The Rayleigh distance is also measured in space, in the plane.
Yeah, it's measured the way it should be. That is, you take your largest frequency and you 1 over that, 1 over it's a Rayleigh distance.
So is it correct to say that the Rayleigh limit is when below the Rayleigh limit, then the convex optimization problem doesn't have a unique solution? The new total variation?
I don't know. It may have a unique solution, but it's not sparse. It's not the correct one.
Did you say something how you solve this total variation problem?
Yes. 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 Because where is semi-definite programming? It's not there. It's missing, right? So that's what we're missing. So maybe I'll skip the noisy results. The noisy results are interesting, but I don't want to keep you away from lunch. So let's skip this.
Okay. The noisy results, you determine the lambda by cross-validation.
You could. So maybe we'll talk about this offline, right? Now, where is semi-definite programming in all of this? All right, so I want to minimize the total variation norm of a measure or sign measure subject to moment constraints. And that the problem is impossible because I have infinite dimensional variable x and finitely many constraints. So I can look at the dual, and the dual of this problem is what I need to find is I need to maximize the dot product between the data vector y, the observed Fourier coefficient, and c, which we'll see are the coefficients of a trigonometric polynomial, such that when I plug this c and put them as a coefficient of a trigonometric polynomial, this trigonometric polynomial is bounded in magnitude by 1. That's a dual. All right, so infinitely many variables x. Now, what's good is the decision variable c is finite dimensional, but infinitely many constraints. So conservation of difficulty. The thing is that this is SDP representable by, sure most of you know this, that I claim that a trigonometric polynomial is bounded in magnitude by 1 if and only if there is a matrix Q which is Hermitian such that Q C C star 1 is positive semi-definite and Q is not anything. The sum along the principal diagonal of Q must be 1 and the sum along diagonals above is 0. Okay, so I say that I have a semi-definite representability. It's easy, and what I'm saying is that checking that a trigonometric polynomial is less than 1 is LMI, is an LMI. And now I have this.
In one variable.
Yes, yes. It's true, it's true in any dimension. A trigonometric polynomial is always an LMI, but there's a degree problem. Okay, it's true in one variable, as Bernd is telling us. That's true. Now I solve this SDP. I solve it. And when I solve the dual problem, I retrieve C. And what do I do with C? I look at this trigonometric polynomial. Remember, it needs to interpolate the sign. So I look at where it interpolates the sign. It's a real experiment with real data and so on. I look at where it interpolates. That's the support of the signal. So to recover the spike location, I'll solve the dual. I solve this SDP. I check when the polynomial takes on magnitude 1. So I have a rooting problem. It's extreme. If you use an inter-point solver, it's nice because the log det pushes you away from the boundary. So you really have like really stuff like this. It's very stable rooting. And then you recover the signal. Okay, so now if I try to explain this in one word, why is this true? Well, why is this result true? I mean, formally, and that's what Bernd is alluding to, is a trigonometric polynomial is non-negative if and only if it's a sum of squares. And that is true in any dimensions, except that when you go in high dimension, you don't control the degrees. But in 1D, it's in fact, you have much more than this. In 1D, you have the Fourier-Ries theorem that says that a trigonometric polynomial is non-negative if and only if it is a square. And so that's why you have the SDP representability, and that's where it's coming from. Okay, so now you get something like this. You get low-pass measurements with an SNR 14 dB. These are noisy measurements. You would like to see the low-res signal, but it's being perturbed because you don't have a perfect microscope, right? And so you get to see something like this. And then you solve the SDP now with noise. And the true signal is somewhere here, which is a bit hard to see. And you solve this SDP, the noisy version of the SDP. And what you do is you pinpoint the location of the sources really well, so you get something like 4 digits of accuracy on the support. Okay, so we do single molecule imaging. We're not going to talk about it. That's my last of my story. 3 problems, 3 SDPs. Seems to work well. So I think it's important to push the theory and algorithm for SDPs because people like me, we use them all the time. Thank you.
There is some time for a few questions only because it's already last Thursday. Any questions in the audience?
You say you can do it on the plane or in the same way?
Exactly the same way.
You don't control the degree?
Right, okay. So we have Pablo and Bernd who know more than I know about this subject. But a non-negative polynomial, trigonometric polynomial, is non-negative if and only if it's a sum of squares. That's true in any dimension. The problem is that in 1D, if I have a polynomial of degree d, or 2d, then the squares will have degree d. In high dimension, I can have cancellations. So their theorem is true, but I don't have a bound on the degree.
I guess in higher dimension you need strict positivity, so it's a sum of squares, right? In dimension 2 it's okay, but in higher dimension you need strict positivity in order to be a sum of squares. But maybe that's not a problem. Because
I don't know. So what I've seen on this topic is a paper by Magretsky. I don't remember seeing strict positivity.
okay.
But
Any other question?
But if you do this, if you solve this SDP, as I mentioned, with just the one you've seen in 2D, it works extremely well. Extremely well. It's like it finds the location of the sources.
Other questions? Time for lunch. Thank you very much.